All right, welcome back. So first up in our series of different rules is the idea of the product rule. As the name suggests, this governs the relationship between two functions that are products of each other and how we take the derivative. So if we define a function f of x as the product of two differentiable functions g of x and h of x, the derivative of f would be g prime h plus g h prime. The idea is we have to take the derivative of both g and h, but we don't do it at the exact same time. When we do the derivative of g, we multiply by the original h function completely left alone, and then plus now we leave g alone and take the derivative of h. Now, because these two situations are adding together, you can do it in whatever order you want. So if we had said f prime was g times h prime plus g prime times h, it's the exact same thing. The order would not matter because we are adding them together. So that's kind of up to you. I personally kind of just see it left to right. The first function derivative, leave the second function alone, and then leave the first function alone, take the derivative of the second function. That's simply how I see it. I think some textbooks show it the other way around. It doesn't really matter. So the idea here is we're going to use the product rule to find the derivative of the given function. We don't want to FOIL this because since we only know polynomial rules, obviously we could just simply FOIL this and take a derivative based off the power rule. But that's not the goal of this lesson. This goal of the lesson is to apply the product rule. This will become a little more apparent, a little more useful, the product rule, when we get into non-polynomial derivatives. When we talk about, again, exponentials, logs, trig functions, all those other ones, this will become a little more useful of a rule. So for right now, we're just dealing with the polynomial rule. So in fact, actually, after we do our derivative, where this is essentially our g of x function, and that's our h of x function, we'd get 18x and then times 5x cubed plus 9. And then we leave the 9x squared minus 3 alone. Derivative h of x is 15x squared. We're going to leave it alone like that. We're not going to do anything else with that. You are certainly welcome afterwards to distribute and combine like terms put into what's called the simplified version of the answer. But just to practice the use of the product rule itself, we're not going to go further than this. You're just simply doing your product rule. One function derivative, other function left alone. And then reverse it. The function you took the derivative of, leave that alone, and then the derivative of the second function. So let's do another one like that. So here again, this would be our first function, g of x. This would be our second function, h of x. So the way the product rule works, we take the derivative of the first function, which is negative 12x squared minus 8, and we leave the second function alone, the 2x squared plus 9x. And then plus, we leave the first function alone, negative 4x cubed minus 8x, we take the derivative of the second function, which would be 4x plus 9. And again, we certainly could distribute and FOIL it. You'll notice we would have to FOIL twice and then combine, which at that point we might as well just FOIL the first term there. So that's kind of why we're just leaving this alone and not worrying about going further with this product rule. All right, so that's all we're really doing with the product rule itself for right now. When we get into those other types of functions, we'll review the product rule in the context of that. But for right now, this is all we're really doing. Now, it also could come in the context of a table. G of x is defined as h of x, h squared times f of x. So according to our product rule, g prime would be 2x times f of x, because it's our first function is x squared, f of x is our second function. So x squared derivative is 2x, leave f of x alone, and then plus leave x squared alone, f of x derivative is just simply f prime. We don't know what f of x is, so all we can do to say the derivative is just say it's f prime of x. So we want to find g prime at 2. So it's 2 times 2, f of 2, plus 2 squared times f prime at 2. So we get 4 times f of 2 is negative 9. And then we get 4 times f prime at 2 is negative 4. We get negative 36 minus 16, which is negative 52. And again, this represents the slope of our function, because we had talked about the tangent line problem and how the derivative represents the slope of the tangent line. So this negative 52 would be the slope of the tangent line to this g of x function at the x value of 2. And in fact, let's get into that a little bit more. Let's talk about equations of tangent lines, because one of the biggest applications, or not necessarily the biggest, but one of the easiest and most recognizable application of the derivative is the idea of the equation of the tangent line. This will happen fairly often. In fact, it's going to happen often enough that you need to be able to recognize that when I talk about derivatives, I'm talking about slopes of tangent lines. And when I'm talking about slopes of tangent lines, I'm talking about the derivative. They are to be used interchangeably and need to be recognized as that. So if I want you to find the equation of the line that's tangent to the curve at a given point, you first find the derivative of that function. Once you have your derivative, you substitute the given value of x into the function. The value will tell you the slope of the tangent line. Now, step 3 kind of depends on the problem. Sometimes you'll be given the full coordinate point, which includes the y value, because you always need slope and a point to write an equation. So you can kind of ignore step 3 if you're given the y value. If you're not, just simply take the given x value, substitute into the original function, that's your y value to find the coordinate point, and then put it into point slope form. Y minus y1 equals m times x minus x1. A lot of times, you won't need to make this as a y equals mx plus b kind of thing by distributing. Everything we do today and everything we do with the polynomial functions, you easily can, because the slope will be an integer, or at the very least a rational number, and same with the coordinate points. Where this gets more interesting and less likely to be used as y equals mx plus b is when the slope and the coordinate points are involving trig functions and exponentials and logs, or they may not necessarily go well together. In which case, leaving it in point slope form is easier to work with, so that's the preferred method. So it just kind of depends. All right, so let's work with the basic one here so we can see our derivative. So to find our slope, because we always need slope and a point, we find our derivative. F prime would be 6x minus 2. We substitute the negative 2 in for x. And we get negative 14. That's our slope. We also need our point, because any equation of a line needs slope and points. So we're given the x value, but we're not given the y value. So the y value is substituting that negative 2 back into the original function. We would get 12 plus 4 plus 1, which is 17. So we want to write the equation of the line which has a slope of negative 14 and a coordinate point of negative 2, 17. So our point slope form would be y minus y1, so the y coordinates, equals m times x minus x1, so it's the opposite sign, and you are perfectly fine leaving it in that format right there. In this particular case, all the numbers are nice integers. It would not be that challenging to have distributed the negative 14 and then add the 17 over to say negative 14x minus 11 would be the slope of this particular line. That would not be wrong to have done. And it's totally up to you whether you need to go that far. I mean, the AP would kind of like give you a hint based off if it's a multiple choice question. If all the multiple choice answers are based on point slope-intercept form or point slope form, you know which one you want to work with. If it's part of a free response style question or you're not taking an AP course where your teacher or professor gives you an option, point slope form is perfectly acceptable and really should be the easiest form to work with. But don't be surprised if you need to do y equals mx plus b when it's in this kind of format right here where they're nice integer values. All right, so that's just a nice simple power rule. So if we look at it in terms of the product rule, though, it's still the same concept. Our slope would be the derivative. So f prime of x would be 4x times 5x plus 4 plus 2x squared minus 1 times 5. We substitute negative 1 into that, so we'd get a negative 4 times negative 5 plus 4 plus a 2 minus 1 times 5. Negative 4 times negative 1 plus 1 times 5, we get 4 plus 5, which is 9. And that's our slope. They have not given us the y value, so we're going to find our point. So the y value would equal 2 times negative 1 squared minus 1, 5 times negative 1 plus 4. So we'd get 2 minus 1, negative 5 plus 4. 1 times negative 1, we get negative 1. So our equation is based off the slope of 9 and our coordinate point of negative 1, negative 1. So it'd be y plus 1, opposite sign always if it's point slope form, 9 times x plus 1. There's our equation in point slope form. And again, if we want to distribute the 9 and then subtract the 1 over, it would not be wrong to have said y equals 9x plus 8. That should be a 9 here. 9x plus 9, not 9x plus 1. All right, so that's all that's happening with the equation of the tangent line. So we did in the video here with the product rule. You can obviously, as we did with example 4, do it based off the power rule. And when we get into, again, the non-polynomial derivatives, you can do it with any one of those rules as well. All you're doing for the equation of a tangent line is finding the derivative, substituting that value in, that tells you the slope, and then using the point to kind of write your equation. Now, it's also something that could be a massively obnoxious question that requires the calculator. Then you're using the n-deriv tool that we had talked about in the previous video and in the calculator playlist to work with that. All right, so that's our product rule. So next up is the quotient rule, which governs the relationship between dividing two differentiable functions. So I'll see everyone next time for that.